So the next talk will be a tag team talk by William Brandon from MIT CSAIL and Ben Driscoll from Stanford. And they'll be talking about how we can improve the efficiency of functional languages through better defunctionalization with Lambda set specialization.
Okay, hello. So, lambdas are expensive. Representations of closure environments typically rely on heap indirection in all but the simplest cases. Calls to lambdas are typically implemented in terms of indirect jumps, which are expensive on modern processors because they interfere with pipelining and speculation. And lambdas prevent program analyses from statically determining the targets of function calls, leading to missed opportunities for compiler optimizations. What if lambdas could be cheap? What if we could represent closures using unboxed stack-allocated structures wherever possible? What if we could implement calls to lambdas in terms of simple jump tables or even fully deterministic static dispatch? And what if static analyses could tightly bound the possible targets of every function call? We're going to tell you about lambda set specialization, a robust general-purpose technique for compiling lambdas which achieves these goals. Lambda set specialization makes lambdas cheap. On a suite of programs in OCaml and standard ML, using lambda-heavy abstractions people care about, like iterators and parser combinators, we find LSS gives 1.9 times and 2.7 times speedups on average. We're about to show you how LSS works, how it fixes problems with the state of the art, and what it means for your next compiler or programming language. So, lambda set specialization is an example of what's called a defunctionalization transformation. Defunctionalization aims to simplify compilation of lambdas by eliminating them from the program. A defunctionalization transform will take a program like the one on the left with higher order functions passing lambdas to each other and transform it to a program like the one on the right in which all functions are first order. In designing a defunctionalization, we don't just want it to preserve semantics, we also want it to satisfy two criteria. We want it to be expressive and we want it to be precise. So what do we mean by expressive? We mean that we want our defunctionalization to be able to handle arbitrary programs in a realistic functional source language. So this means that we want to be able to gracefully handle a whole range of language constructs, like we want to be able to handle when code returns a different lambda from each arm of a conditional branch. We want to be able to handle higher order functions which use lambdas as return values, not just functions which take lambdas as arguments. We want to be able to handle recursion, including mutual recursion, and complex cases like this one, where a lambda recursively captures other instances of itself. And we want to be able to handle lambdas being used not just as bare values, but also inside data structures, including user-defined data structures and recursive data structures, like this linked list. And when we say we want to be able to handle these constructs, what we mean concretely is that first, our defunctionalization shouldn't ever refuse to compile well-typed source programs that use these constructs. But we also mean that we should try to use unboxed environments wherever possible and fall back to heap indirection only when absolutely necessary. And finally, we mean that we actually want to avoid indirect jumps, not just in some cases, but actually in all cases, always preferring jump tables over fully generic virtual dispatch. And when we say that we want to be precise, what we mean concretely in the context of this talk is that we want to avoid something which we're going to call poisoning. So poisoning is when adding a new call to a function somewhere in your program can degrade the precision of optimizations, add unrelated calls to that same function elsewhere in your program. So let's look at a simple example to see what we mean. So suppose we have a program containing functions f and g is a higher order function. So f calls g, passing it a lambda. And suppose that when we defunctionalize this program, the resulting functions, f prime and g prime, optimize well, and they have good performance. But suppose that now we add a new function h, which also calls g, and it passes it a different lambda. If our defunctionalization is subject to poisoning, then adding h might change g prime. And this might in turn degrade the performance of f prime. So h prime has poisoned g prime and indirectly poisoned f prime, even though f might be in a totally different part of the program than h. So one of our main observations is that if you want to avoid this poisoning effect, in a sense the only way to get around it is to instead do specialization. So if h had introduced a new specialized version of g, say g prime prime, instead of modifying the existing g prime, then we could have avoided poisoning. So by precision, we basically mean that we want our defunctionalization to be able to apply this kind of specialization.
Thanks, William. So now we're going to build up some intuition for our technique, and we're going to do that by way of an example. And we're going to start out by looking at prior techniques, how they handled this example, where they fall short, and how we can fix those shortcomings. So prior defunctionalization passes can be divided into two camps, specializing passes and non-specializing passes. We'll take a look at these two different classes of defunctionalization transformations by way of our example. So our example will be the map function over lists, and it will have two call sites. At one call site we'll pass f, at the other call site we'll pass g. Specializing defunctionalization can be commonly found in systems programming languages like Rust and C++ as the crucial optimization that makes lambdas fast. And users can opt into this in those languages. So how would languages like Rust and C++ compile our example? Well, that's simple. They just produce two different separate implementations of our map function, one using f substituted for lam, one using g substituted for lam. That's map 1 and map 2 on these slides. So this transformation is simple. It passes our precision desiderata with flying colors. But let's return to the example and consider what happens when we make it just a tiny bit more complicated. So instead of passing g for lam, at the second call site of map, let's try passing the result of a conditional, either g or h, depending on some runtime value. Unfortunately, no prior specializing technique can handle even the simple extension to our example. So in summary, while prior specializing work features excellent precision, it falls well short of our desired expressiveness. Now let's return to our example, but this time let's talk about non-specializing passes. The earliest defunctionalization technique, which was introduced by Reynolds in 1972, was non-specializing. And usually when people talk about defunctionalization, this is the type of pass they're thinking about. So how would a language that uses a non-specializing defunctionalization handle our example? Well, what the language would do is run a flow analysis and determine all of the lambdas that can flow into lam. In this case, f, g, and h can flow into lam. Then it would replace lam with a sum type with 3 variants, one representing each of these possible values. And then the call to lam becomes a match on this sum type. So this has great expressiveness, good so far. What's the problem? Well, you may have noticed something. We just experienced poisoning. The call to map which passes f is unrelated to the call to map which passes g or h. Yet everywhere we call map, we match on a sum type that has 3 variants. So we're being conservative over the behavior of all these possible lambdas everywhere. Imagine you have a 1,000,000-line code base that calls map all over the place. This just isn't scalable. In summary, while prior non-specializing techniques feature excellent expressiveness, they fall well short of our desired precision. Because, like we discussed, we don't want poisoning. Again, let's return to our running example. But this time, let's think about what we'd like the output to look like. So if we'd like to maintain expressiveness, we still need to use this sum type technique from Reynolds style work. But can we somehow find a way to use this sum type trick and recover expressiveness? Or recover precision, sorry, recover precision. Well, sure. We can still specialize our code, but this time, instead of specializing with respect to a lambda at each call site, we'll specialize with respect to a sum type. At the first call site, we passed 1 lambda, so we get 1 variant. And at the second call site, we might have passed a G or H, so we get a sum type with 2 variants. So now we're going to talk a bit more in detail about RPass, LSS, and how it's able to achieve this sort of output. The starting point for LSS is to view defunctionalization as type inference. To that end, we define a compiler internal type system, invisible to the user, for which type inference never fails. We'll see in the next few slides why this is a useful framing for defunctionalization. For each function type in our source language, our internal type system includes a bit of extra information, a lambda set annotation over the arrow which tracks which lambdas can flow into values of that type. So how do we achieve expressiveness? Well, as the name implies, lambda set annotations track sets of lambdas. If, for instance, we have a conditional and the lambda which flows into a given value depends on the condition, we just track both possibilities in the set. Also, we can use lots of standard type system tricks to help us encode more complicated constructs. So, for instance, we introduce a least fixed point operation at the level of lambda sets to handle recursion. Now let's talk about how we handle precision. The key idea is to allow functions to be polymorphic over lambda sets. This lets us do a single analysis of each function in terms of abstract lambda sets, and then reuse that analysis at each call site to generate a specialized implementation. We get all the nice compositional results we want because we're using a type system. And notice how specialization is extremely natural in this setting. If we pass 2 lambdas at 2 different call sites, well, we just do good old-fashioned type monomorphization with respect to concrete lambda sets. Once we have our specializations and all the lambda sets are concrete, lowering them is easy. So types guide defunctionalization. If we see a type annotated with a 2-member lambda set, we simply turn the underlying value into a sum type with 2 variants. And we turn calls to that value into matches on that sum type. Now that we understand lambda set specialization a little bit better, let's return to our map example one final time and run through how LSS handles it. First things first, we infer a polymorphic signature for map in our annotated language. The lamb parameter is a lambda, so it needs a lambda set annotation. Since map is polymorphic over sigma, we need to make sure to plug in the right sigma each place we call it. At the first call site, that's a set just containing F. And at the second call site, that's a set containing F and G, or G and H, sorry. Great. Now that each call site plugs in the right lambda, avoiding poisoning is easy. For each sigma that gets plugged into map, we generate a specialized implementation. Finally, types guide defunctionalization. Our first call site passed a singleton set, so its implementation of map matches on a sum type with a single variant. Our second call site passed a set with 2 members, so its implementation of map matches on a sum type with 2 variants. Through LSS, we have obtained exactly our desired code. Our transformation is simultaneously expressive and precise. As you may have guessed, there are lots of details which we couldn't include in this talk that are necessary to really make this type system work and to achieve all the expressiveness that we want to achieve. I encourage you to read the paper for details. And now I'm going to hand it back to William so he can close out the rest of the talk.
Okay, hello. So we haven't just worked this out theoretically. We've actually implemented it in practice. And we tried applying LSS in the setting of 3 compilers. The standard OCaml compiler, the Milton compiler for standard ML, which actually by default has a non-specialized defunctionalization built in, and Morphic, a new functional language and compiler which we designed from the ground up to take advantage of lambda set specialization. So we ran LSS on 6 benchmark programs in all three of these languages, and we saw speedups across the board. So these benchmarks all use library abstractions that rely heavily on lambdas. The primes benchmarks and quicksort use a lazy iterator abstraction. The unify benchmark uses a state monad library. And calc and parse JSON are implemented in terms of parser combinators. And we see that only a single program here gets slower, and by only 10%, while the best performing benchmarks under existing compilers improve by up to about 7 times, and the best programs in Morphic improve by almost 80 times. So it's worth noting that parse JSON here, which sees the biggest improvement due to lambda set specialization, is also our largest and our most realistic benchmark. So on average, OCaml and Milton improve by 1.9 times and 2.7 times, and Morphic, which we designed from the beginning to take advantage of lambda set specialization, improves by 12 times. And again, keep in mind that for Milton, the baseline we're comparing against here is already using a state-of-the-art non-specializing defunctionalization. So the gains we see for Milton are all from the specialization aspect of LSS. And since we're doing specialization, you might worry that LSS will increase binary sizes. It turns out that LSS increases binary sizes a bit for some programs, but never by more than 35% on our benchmarks. And it actually decreases binary sizes in many cases. So in OCaml, binary sizes increased by 11% on average, but for both Milton and Morphic, binary sizes were smaller on average after applying LSS. So the optimization benefits of LSS can more than compensate for the costs of specialization. At a higher level, we learned 3 big lessons from applying LSS in practice. The first is that LSS is really powerful for enabling downstream compiler optimizations. This is largely because LSS creates a lot of opportunities for inlining. But in Morphic, we also found that LSS made it possible for us to implement very precise interprocedural optimizations that would have otherwise been basically infeasible. We also found that LSS obviates the need for many more specialized optimizations designed for functional languages. If you combine LSS with a generic optimization framework like LLVM, you can get the same effect as if you used classical functional optimizations like stream fusion or higher order inlining. And finally, and maybe the most interesting thing from a PL design standpoint, is that LSS makes it possible for user space library code to define new zero-cost abstractions. In a language which uses LSS, users can define very rich and expressive library APIs based on higher order functions while maintaining confidence that they'll get the same performance as if they'd written the equivalent first order code by hand. So in summary, we observe that it's really important that defunctionalization be expressive and precise. And we introduced Lambda set specialization, which uses a compiler-internal polymorphic type system to achieve these goals. LSS simplifies and improves compiler optimizations for languages and programs with lambdas, and we find that this enables big speedups in practice. And we believe that LSS is production ready. We encourage you to plug it into your next compiler or programming language, and we can't wait to see what you do with it. And I think with that, we'll open it up to questions. And you can go to this QR code.
Hi, thanks for the great talk. This is Rajat from Cornell. So one way that I was thinking about this work is that it recasts the problem of defunctionalization as monomorphization. It seems like it could have some fun consequences for people building type-preserving compilers, where you might have to verify sort of, that your defunctionalization lowers your types correctly. Now, if you can use your technique, maybe you can recast it as a simpler sort of monomorphization pass. Can you sort of comment and maybe think out loud about this a little bit?
Yeah, so the question is there some relationship between the fact that we're using a type system to do our defunctionalization and the goal of trying to achieve type-preserving compilation in compilers that do defunctionalization? I think the answer is absolutely yes. So if you look at the prior work on non-specializing defunctionalization, there's actually quite a lot of work that grapples with, in that setting, the quite difficult problem of preserving types and of producing well-typed output programs. The original technique by Reynolds did not preserve types. There was follow-on work that will essentially group lambdas by types to ensure that you never have 2 lambdas with different signatures that get put in the same set. There's various follow-on work on getting that all to work in the presence of polymorphism. And in a sense, we get all the benefits of type preservation just for free, because the particular precision properties of our specialization mean that basically, you'll never add 2 lambdas to the same lambda set unless they provably have the same signature. And definitely, you could, in a formal treatment, you could prove that that property always holds. But I think it's a general benefit of these kind of techniques that they sort of preserve types automatically and by default.
Thanks.
So we have a question from online, so I'll add in on Discord. Okay, so interesting talk. Could you go into how Lambda set specialization differs from continuation passing style and optimizations from there?
From what optimization passes in particular?
Continuation passing style and optimizations from there.
Continuation passing style, right. So the question is, how does Lambda set specialization differ from or relate to continuation passing style? So I would actually say that translations of programs into continuation passing style are largely complementary with Lambda set specialization. And in fact, so we have an ongoing collaboration with the open source ROC programming language, ROC, where they've actually implemented Lambda set specialization, and they're using it largely in the presence of sort of effectful async code in which you have these sort of suspend points that save continuations. And depending on exactly how you encode continuations into a library that, or into like programming patterns that use them, LSS will do different things, and there are various engineering trade-offs there that let you basically trade off between the performance cost of resumption and the number of different specializations that you get, and the details of that, if anyone's interested, you can meet me after. But I would say that basically continuation passing style usually assumes the existence of sort of traditional dynamic lambdas that you can pass around, and doesn't really do the sort of devirtualization that we do by design. And so it's complementary to ours because we can devirtualize that kind of code.
Thank you. Very nice talk and very elegant work. I'm Alessio Sergey from NUS. Okay, so here's something I would like to understand better. So any attempt to do specialization and Reynolds-style defunctionalization will most likely require you to do some version of interprocedural higher-order control flow analysis like zero CFA. And that thing has a cubic complexity. And you show a type system for specialization which is compositional, so should have linear complexity in the size of the program. So could you please comment on this? So do you sacrifice precision, or how does it work?
Right, so the question is, how are we doing an interprocedural analysis while maintaining good time complexity in the analysis and preserving precision? So I think, part of this is that our technique is kind of decoupled into these two phases. There's an initial like bottom-up analysis phase in which we are annotating every higher-order function signature in the program with one of these polymorphic lambda set annotated signatures. And then there's a separate phase where we specialize. And these actually have quite different worst-case runtime complexities. So the analysis phase, as you correctly observe, is basically linear time because we're just we're running sort of local type inference to infer like a principal polymorphic type for every definition in the program. The specialization phase, as it is in almost any specializing system, as it is with like C++ template specialization or Rust generic monomorphization, it's worst case exponential. Because you can construct pathological examples that will result in sort of an exponentially large tree of specializations. In practice, we find that this is fine on our benchmarks, and we think the examples that would trigger that are quite are sort of edge cases that are unlikely to occur in practice.
So just to clarify, your signature doesn't require to compute full-blown flows to information.
A full-blown what? Sorry.
Flows to information.
Right, so it's an abstract information flow analysis in terms of sort of a symbolic parameterization of any contextual information from the call site. I don't know if that answers your question.
All right, let's take offline. Thank you.
Okay, sounds good.
So clearly this talk is causing a lot of interest, but the show must go on. So I suggest you speak to the speaker afterward, and then we go on to the next talk.